Welcome back to AI on AI, the show where algorithms meet the boardroom, sometimes politely, sometimes with fireworks. Today, we're cracking open Q-chunking, a new recipe for offline to online reinforcement learning that's making waves in long-horizon, sparse reward tasks.
Glad to be here. I look at this from the COO chair. Faster learning means faster ROI, and Q-chunking claims to chop wall clock time by an order of magnitude. So, yes, my ears perked up.
Same here. From a research lens, the beauty is that it fuses action chunking, traditionally an imitation learning trick, into pure TD methods without the bias plague of naive end-step returns.
And on the robotics floor, we're seeing it translate to smoother trajectories. Think of it like giving the robot jazz sheet music instead of single notes. It just grooves.
I'll jump in. The math behind that groove is the critic operating in the extended action space. By feeding the entire H-step sequence, you maintain an unbiased value target while still propelling information H steps back.
I'm wearing the investor hat, so the key metric for me is sample efficiency. Each real-world industrial robot hour costs about $150 all in. If Q-chunking can cut training hours by 40 to 50%, that's venture scale impact.
Love the framing. Let's unpack the sauce. First, technical deep dive. How exactly does the critic escape the off-policy bias that haunted earlier end-step methods?
Sure. Classic end-step backs up QSA with a sum of rewards plus QS-A claw. If your stored actions diverge from the current policy, you're baking in distributional mismatch, bias. In Q-chunking, we upgrade Q's signature to QSA1 because the critic sees the entire executed chunk, the target distribution matches the stored one, bias vaporized.
Building on that, the H-step propagation accelerates credit assignment. On our cube quadruple benchmark, value signals traveled 25 time steps per update instead of 1. Think broadband versus dial-up.
Let me translate that to dollars. In a warehouse palletizing pilot, we logged 600K fewer physical actions to hit 90% success. That shaved 3 weeks offline downtime.
Plus, the behavior constraint is sneaky powerful. Using a flow-matching prior and best-of-n sampling, you implicitly enforce a KL bound. N becomes a knob, turn it up for exploration, down for safety.
Quick analogy. Think of N like the number of audition tapes you screen before casting a lead actor. More auditions, higher odds of a star, but you burn more time.
Nice. Second deep dive. This best of N trick. Some folks call it expected max. What makes it computationally sane?
The key is reuse. You sample N candidate chunks from the flow prior in one forward pass. Then a single critic eval picks the winner. Complexity grows linearly with N, not exponentially with Horizon. We tested N equal 32. Overhead was 50% versus vanilla, yet rewards doubled.
And the hardware synergy is real. GPUs fondly batch those N evaluations. On an RTX A5000, we clocked 15 milliseconds per online step, peanuts relative to robot cycle time.
Still, CFOs will ask, can't we just crank up simulator training? The answer is, Sim2 real gaps remain. You want every real action to count, which is Q-chunking's raison d'etre.
Exactly. Offline data provides structure. Online fine-tuning injects reality. Q-chunking stitches the two with temporally coherent exploration. Less herky-jerky, more ballet.
Here's a live business case. An agritech firm used Q-chunking to fine-tune berry-picking arms. Yield per hour climbed 18% because the arms stopped dithering between berries. They committed to coherent pluck sequences.
I'm picturing robot sommeliers next. Third deep dive. The flow-matching behavior model and Wasserstein regularization in the QCFQL variant. Why not just stick with Gaussian policies?
Ha! A Gaussian is like describing the stock market with mean and variance. Good luck. Human teleop data is multimodal and non-Markovian. Flow matching learns the transport map from noise to that complex distribution. The Wasserstein 2 distillation gives us an upper bound we can optimize in closed form. And because the policy is noise conditioned, you can amortize exploration. One network call, one latent, whole chunk, no RNN bookkeeping.
We ran an ablation, swap the flow prior for a Gaussian, keep everything else. Success on cube triple nosedived from 72% to 15%. So yeah, expressivity matters.
Strategically, this means enterprises should archive teleop and scripted logs instead of discarding them. They become behavioral gold.
Data is the new oil, as the saying goes. But I'd add, structured data is premium unleaded. Q chunking refines that fuel.
All right, contrarian corner. What's the hidden gotcha no one's talking about?
I'll take the heat. Everyone gushes about fixed chunk lengths, but if your environment dynamics change mid-chunk, say a human walks into the robot's path, you're flying blind. Adaptive, variable length chunking is still an open problem.
I see your point, but we've mitigated that by introducing an emergency interruption trigger monitored at 10 Hz. If safety flags, we break the chunk and replan.
Still, variable chunks would let the agent learn when to pause versus power through, sort of a learned tempo.
From a governance angle, regulators will eventually demand introspection hooks. If a 6-action chunk involves 3 safety-critical steps, auditors need transparency.
Which opens opportunity, compliance as a service for RL pipelines. First firm to package that wins big.
Let's zoom out. Future roadmap. Where does Q chunking go in the next 24 months?
2 words, latent chunks. Encode sequences in a smaller latent, let the actor operate in that space for even faster planning. And combine with model-based rollouts. Do Monte Carlo tree search over chunk latents, AlphaZero vibe, but for manipulation.
On the shop floor, I foresee cross-task transfer, pre-train chunks on assembly, fine-tune for packaging. Early experiments show 60% retention of policy performance.
That's essentially software-defined robotics. You'll license skill libraries the way we license ERP modules.
Valuation-wise, this shifts robotics from CapEx to OpEx. Investors love recurring revenue, SaaS for motion control.
Closing round. 1 heuristic each for leaders tuning Q chunking in production.
For engineers, start with H equals 5. If learning stalls, double H before tweaking anything else.
For operations teams, monitor temporal coherency metrics, the average L2 of consecutive end effector points. Spikes signal jittery exploration.
For data scientists, use the 80-20 rule on your offline set. 20% of trajectories often capture 80% of coherent behavior. Prioritize those for the behavior model.
For executives, set a KPI on sample efficiency, not just final accuracy. What gets measured gets managed.
And for investors, diversify risk. Bet on tool chains that support adaptive chunking so you're future-proofed.
Fantastic. In theory, there is no difference between theory and practice. In practice, there is, said Yogi Berra, and Q chunking seems to blur that line nicely. Thanks to all our experts and to our listeners. May your value backups be fast and your action sequences smooth. See you next time on AI on AI. Welcome back to part 2. Grab your coffee, we're rolling up our sleeves to talk implementation details and yes, how to pitch them to the CFO.
Let's kick off with the critic architecture. Under the hood, we're looking at a feed-forward MLP with 4 hidden layers of 512 units each. But the trick is concatenating the state vector with a flattened HA action tensor. That changes the dimensionality, so weight initialization matters. We used orthogonal init plus layer norm to prevent exploding gradients during those H-step backups. Right, and notice the ensemble aspect. K equals 2 works for most tasks, yet bumping to K equals 10 on cube quadruple cut variance in the target by roughly 35%. For practitioners, ensemble size is where you trade memory for stability. 1 GPU per 5 critics is a good heuristic.
Piggybacking on that, we found that an update to data ratio of 1 was sweet spot. Push it to 5, and you saturate GPU compute while the robot sits idle, which defeats the purpose of sample efficiency.
Translating to business, that means your robot and compute stay in lockstep, no idle assets. We estimated $12 K monthly savings just by ditching those wasted cycles in a packaging line.
And that's before you factor in opportunity cost. Faster fine-tuning means earlier market entry. In consumer electronics assembly, a 6-week head start can equate to 2 to 3% additional market share for a holiday season.
Implementation question I keep hearing. Do we really need flow matching? Couldn't we bootstrap with a simple VAE?
You could, but flow matching gives you an invertible map, so best of n sampling pulls from the true high-probability manifolds. VAEs tend to blur modes. Your chunk samples will look like average behavior, not crisp strategies. In practice, success rates dropped from 78% to 52% on scene sparse when we tried a VAE prior.
Plus, flow matching dovetails nicely with the Wasserstein regularizer. The closed-form upper bound on W2 gives a tunable alpha that's linear in compute. You're not solving an extra optimization loop.
To implement flow matching, you only need an Euler ODE solver. 10 integration steps sufficed. Going to 20 gave diminishing returns. Only a 1.5% uptick in policy quality at double the runtime.
For ops managers, that means no exotic dependencies. PyTorch's native autograd and a tiny ODE loop handle it.
Let's pivot to chunk length. H=5 was your default, but how do teams choose?
Start with task latency. If your conveyor belt moves an item every 1.5 seconds and you issue actions at 20 Hz, that's 30 time steps, a chunk that captures 15 to 20% of that horizon, so H5 is a solid starting point.
And monitor TD error variance. If variance spikes, your chunk is too long relative to model capacity, shorten it.
Conversely, if the policy dithers, low temporal coherency metric, we usually bump H by 2. It's like adjusting shutter speed on a camera. Longer exposure smooths the motion blur.
The business framing is simple. Longer chunks equal bolder bets. In highly regulated pharma packaging, we stick to smaller H for tighter control, whereas in e-commerce sortation, we can afford longer bursts for speed.
Storage footprint. 100M transition datasets sounds scary. How did you manage that for Cube Quadruple without melting DRAM?
We sharded the dataset into 1M transition chunks on disk with ZST decompression. Only one shard is memory mapped at a time. Each shard loads in Y0.8 seconds, and we swap every 1,000 gradient steps.
Important nuance. Because the critic sees full action sequences, shards remain IID enough. We didn't observe catastrophic forgetting across shard swaps.
We paralleled that in a live forklift automation pilot. Edge devices held only a subset of historical logs and still reached production policy in 4 days.
On the safety side, we integrated an interrupt controller. Chunks execute open loop, but a low latency reflex policy can preempt if force sensors exceed thresholds. Implementation-wise, it's just a priority queue in the control stack.
Exactly, and because the RL policy logs where it exited prematurely, we feed those transitions back offline, closing the loop.
I like that it's the Deming cycle for robots. Plan, do, check, act.
And from a boardroom perspective, those reflex overrides hit the key risk metrics investors care about. Time loss incidents, mean time to recovery, insurance premiums, down by 11% after rollout in one facility.
Quick contrarian nugget. Everyone praises best of n, but beyond n=64 returns plateau, while compute climbs linearly. So resist the temptation to just crank n, profile first.
We tested n=4 on the berry picker scenario and still beat Gaussian SAC by a mile. Sometimes less is more.
The 80-20 rule again. 20% of candidate chunks deliver 80% of the gains.
Before we wrap, give the audience a deployment checklist.
1. Verify your offline dataset covers at least 3 times the state space diameter of your target task. Otherwise, exploration will stall.
2. Calibrate over n on a single validation task. Port the same values across tasks to avoid hyperparam hell.
3. Instrument temporal coherency and TD error dashboards from day one. What you don't monitor will bite you.
4. Line up cross-functional buy-in early. RL fine-tuning touches data, ops, and safety teams. A weekly stand-up saved us endless email threads.
5. Budget for GPU cycles, not just robot hours. A 50-cent cloud GPU minute is cheaper than a $150 robot hour. Use Cloud Burst to accelerate offline pre-training.
That's a playbook right there. Plans are worthless, but planning is everything, Eisenhower said, and Q chunking adds a new arrow to that planning quiver. Thanks again, Dream Team, and to our listeners, may your critics be unbiased and your chunks coherent. Catch you on the next AI on AI. Hold up, team. Listeners are pinging us for a rapid-fire recap, so let's squeeze in one last lightning round of biggest takeaway in 20 seconds or less before we officially drop the mic.
Sure thing. Core Innovation is running RL directly in a chunked action space. That single design choice unlocked unbiased H-step TD backups and gave us those eye-popping sample efficiency numbers.
From a systems lens, pairing that with flow-matched priors and best-of-end sampling is what keeps exploration on policy enough to stay stable. Think of it as a dynamic safety rail, not a hard cage.
I'd add that temporal coherency metric, simple L2 on end effector deltas, turned out to be the canary in the coal mine. Watch it, and you'll catch drift long before reward curves sag.
Implementation highlight. You can bolt this onto existing TD3 or SAC stacks with maybe 200 extra lines of code, most of it loading shards and flattening the HISA tensor, so barrier to entry is low.
Strategy angle. Because offline to online fine-tuning now happens in days, not weeks. Execs can iterate product features in the same sprint cadence as software. That's an organizational game changer.
Beautiful. Earlier we promised an end-to-end summary, so here it is. 1. Leverage existing offline logs. 2. Pre-train critic and flow prior. 3. Shift to chunked action space. 4. Enforce behavior regularization via implicit KL or explicit Wasserstein. 5. Fine-tune online with best-of-end sampling. And 6. Monitor coherency plus TD error for governed rollouts.
And don't forget the contrarian nugget. Scaling N blindly isn't free. Profile and stop at the 80-20 inflection.
Same goes for chunk length. Match it to task latency, not some arbitrary 5 is cool rule.
Plus, shard those monster datasets. Smarter I/O beats bigger RAM every time.
Finally, integrate reflex overrides so open-loop chunks don't sacrifice safety. Cheap to implement, priceless when the unexpected happens.
Wrap this all in a cross-functional governance model, and you'll see ROI that finance actually believes.
There we have it. Key innovations, practical heuristics, and board-level value, all in one show. As the saying goes, innovation is the ability to see change as an opportunity, not a threat. Q-chunking turns the change in action representation into exactly that opportunity. Thanks to all our experts, thanks to you, the audience, and until next time on AI, keep those agents learning.